this next chapter, chapter 3, we're going to be dealing with volumes of revolution in cross-sectional areas. And the first section of chapter 3 is called the disk method. So let's say that we have a function y equals f of x, and it's bound by the vertical lines x equals a and x equals b. And we want to take this region R, you can see it's shaded in the diagram, and we want to rotate it around the x-axis, building a three-dimensional solid object. Well, if we rotate it, you'll see the different progressions as it rotates around the x-axis, and we end up getting a three-dimensional, like a solid cone at the end that is a three-dimensional object, okay? And our goal is going to be to find the volume of this three-dimensional object. So let's take a look at an example and see if we can come up with a way that we can do this. So say we have the curve y equals x squared, and the curve y equals x squared, the region R is bound by that curve y equals x squared, the x-axis, and the two vertical lines x equals 0 and x equals 2. So if we draw a sketch of our function here, first of all, we know when x is 0, 0 squared is 0. When x is 1, it's 1. When x is 2, it's going to be 4. And if I was to draw in that region, I would get a parabola. Now, the region R is cut off from 0 to 2, and it said the x-axis. So there is my region R right there. And I want to revolve this region around the x-axis. Okay? Well, if we think about this, if I take one slice from this region and I draw the slice perpendicular to the axis I'm rotating around, notice that that slice does touch my axis of rotation. So if I was to spin that one slice around the x-axis, I would get a solid disk. So it would kind of go around and come back. I would get a solid disk. So a disk is a circle, and we all know how to find the area of a circle. So if we could find the area of the circle, that would give us the area of the one disk. And if I integrate from 0 to 2, that would give me the areas of all the disks. And if I add up all the areas, it's going to give me the volume of my three-dimensional object. So to find the volume, okay, the volume of a circle we know is the volume of my region is going to be the integral going from 0 to 2, because that's where I'm drawing my slices from. And the object that I form when I rotate one slice of my region R around the x-axis is a circle. So my equation for the area of one circle is pi r squared. And I'm going to be integrating with respect to x because I'm rotating around the x-axis. Now, my radius is simply the length of this slice, and the length of this slice is defined by the function y equals x squared. So, to figure out the radius, it's going to be pi. Well, the radius is just my function in this particular case, so it's x squared, and I have to square it because it has to be radius squared, and I'm integrating with respect to x. So to simplify this, quite often they'll bring the pi out front because pi is a constant. And if I square my x squared, I get x to the fourth dx. And now it's just a matter of answering or performing the calculations for this integral. We should know how to manually integrate that, but just to save some time, we're going to use our calculator. Okay, so I'm going to calculate. And I want to do a definite integral, and I'm going from 0 to 2 of my function, and when I simplified my function it was x to the power of 4, so it's going to be x raised to the power of 4, and I'm integrating with respect to x. And if I get my answer, it works out to be 32 over 5. So the answer to my integral is going to be pi times 32 over 5, which is going to be 32 pi over 5 would be the area of my the volume of my three-dimensional object. So basically, what we have to consider when we're doing the disk method is ask yourself, does my slice in my region touch the axis of rotation? And if it does, when I rotate it around the x-axis, it's going to form a disk, and the area of a disk, which is a circle, is pi r squared. And I determine the radius from my function, and then I work it out. So, in general, the volume of a solid of known integrable cross sections area AX from x equals A to x equals B is equal to the following formula. So volume equals the integral from A to B of the area of the shape of my object that's being rotated around the x-axis, which in this case is always going to be a disk. Okay, let's try another example. So we're asked to find the volume of a solid formed by revolving the region f of x, which equals root sine x from 0 to pi, and we want to rotate this about the x-axis. So it might be handy to get a picture of this. So I want to graph the square root of sine x. Whoops. Sine, what did I do there? Of sine x and I'll graph that, and I end up getting, looks like semicircles. Okay, so if we were to transpose that onto our graph, I'm going to get a region that looks something like this, and it happens to work out that this is 0 going all the way to pi, okay, and that's going to be the region that I'm looking for because it's bounded by those two values right there. So now they want me to revolve this region R, and it's the region bound by the red graph and the x-axis, and they want me to revolve this around the x-axis. So I'd like to use a bit of a different color here if I can draw my slice, and there's my slice touching the axis of rotation, and again I'm rotating around this axis. So therefore that's going to be my radius, and the radius in this case is just my function, which is root sine x. Now my radius will change depending where I draw my slice, but again it's still going to be defined by the function root sine x. So when I find the volume, it's going to be the pi, I'll just move the pi out front right away, the integral from 0 to pi of my radius squared. Well, in this particular case, my radius is the function root sine x, so it's root sine x all squared dx, and this works out quite nicely because if I square a root, the root disappears. So basically I need to integrate sine from 0 to pi and evaluate that and times it by my constant pi. So again, we'll use our calculator here. So we'll go back to our calculate screen, and we want to do a definite integral from 0 to pi. Whoops. Sorry about that. From 0 to pi. And I don't know what's going on here. And my function is sine x dx. And that works out to be 2. So my integral is 2, and if I times it by the pi out front, my final answer for my volume would be 2 pi. So if I rotate this whole red region around the x-axis, I'm kind of going to get a football-shaped object. It would have a volume of 2 pi. Okay. These next couple of questions are from AP exams way back from 1998, so I'm just going to leave these two right now. And let's try one more example. And in this example, we have the function 2 minus x squared and the function x equals 1. And now we're going to revolve that region bound by these two curves around the line y equals 1. So we're changing our axes of rotation. Okay, so if you think about the function 2 minus x squared, that's just a parabola that's been inverted and shifted up 2 units. So I'm going to spread this out a little bit. So I'm going to make this 2 right there, and there's going to be my function f of x, which is 2 minus x squared. Now my function g of x, which I'll do in red, is going to be the horizontal line right there. And this happens to be my axis of rotation as well. So this region bound by these 2 curves is going to be my axis of rotation. So this is my region R right there. And if I wanted to draw a slice in that region, there would be my slice, and again, it doesn't matter where I draw my slice, so that's my radius, and it is touching my axis of rotation. Now, had this slice been being rotated around the x-axis, then this would not be a disk method because my slice is not touching my axis of rotation, but in this case it is. Now, the first thing I need to do is I need to find my intersection point. So just like we did with area, we could do this algebraically by equating our 2 functions. And if I add the x squared over and subtract 1, I get x squared equals positive 1. And if I square root, it works out that my x-intercepts are plus or minus 1. So those are going to become the limits of my function. So now to find the volume when this region R is rotated around the line y equals 1, it's going to be pi, the integral from -1 to 1 of whatever my radius is squared. Now, the radius is going from the top of this slice to the bottom of this slice. And the top of the slice is the function, which is 2 minus x squared. So the top of this is 2 minus x squared. And then you have to subtract away what the bottom of the slice is touching, and it's the function y equals 1. So if I simplify that expression, it becomes negative x squared minus 1 is my radius. And I still have to square it, and I have to integrate that with respect to x. So now we'll go back to our calculator. And again, hopefully it cooperates this time. So I have the definite integral going from -1 to positive 1. And my integrand was negative x squared minus 1. So negative x squared minus 1, and I'm integrating this with respect to x, and that works out to be negative 8 pi over 3, which can't be possible because I can't have a negative. So what did I do wrong here? This should have been plus 1. My mistake. So let's go back and change that. So we'll try that again. So this is going to be -1 to positive 1, and my integrand is negative x squared plus 1 with respect to x, and now I should get an answer of 4/3. That's better. Now that's the answer to my integral, so if I times it by the pi, my volume is going to be 4/3 pi. So we don't always have to rotate our region around an x-axis. Sometimes we can rotate it around a different line, but provided our slice touches the axis of rotation, we can still use the disk method. Okay, what happens when we go around the y-axis? Because remember how we found area using integrating with respect to the y-axis? Well, the same thing can be done with volumes of revolution. So let's take a look at this here question. It says the region R in the first quadrant bounded by the function y equals x squared. So if we draw a quick sketch, here's y equals x squared, and the line y equals 4. Well, y equals 4 is a horizontal line right there. This is y equals x squared. And now it says find the volume if region R, and this is my region R, is rotated or revolved around the y-axis. So again, we have to now draw our slices perpendicular to the axis of rotation. And now we're rotating around the y-axis, and my slice is touching my axis of rotation. So now my slices are going from 0 to 4. So the only difference is, because I'm rotating around the y-axis, I have to get my equations in the form x equals. So my slices are defined by this function right here. So I need to get this in terms of x equals, so square rooting both sides. I would get plus or minus root y is equal to x. And in the first quadrant, we are dealing with the positive branch of that. So there is my function in terms of x, and that's really my radius. So now to find the volume of this three-dimensional object, it's going to be pi. Now my slices are going from 0 to 4, so we use our y-axis to get our limits. And it's going to be my radius squared, and now I'm integrating with respect to y. So now I am going to plug in the radius. Well, the radius we already said was the function root y, and if I square that, it works out quite nicely. It just works out to be the integral from 0 to 4 of y dy. And again, because I'm lazy, I'm going to use our calculator. So we're doing the definite integral from 0 to 4, and my function is y. And I'm integrating with respect to y, and that answer is going to be 8. And so my final answer, when I times it by my constant, is going to be 8 pi. All right, so that is how we deal with volumes of revolution that are going around the y-axis. Now, in 2016, if you look at the AP exam, there was a question that dealt with a disk method. And we'll go through this when we start reviewing for the AP exam, so I'm going to just leave this for now. But there's a short assignment from your textbook on page 392. So again, if you have any questions, feel free to ask, and good luck with the assignment.